Let's talk about timers and counters. Both are functions in PLC programming languages that are very useful indeed. Counting items is a very important task. Timing events is very important. And so you'll see timers and counters on any PLC type that you encounter. But they're similar things in that a counter counts events whereas a timer counts up time. Now, a timer automatically runs, right? Time goes on, and so it counts up as time goes on. And often there are, in fact, of all that I know, there are free-running clocks in PLCs. So that when you turn them on, sometimes they'll, be newer ones are based on dates. Older ones, the date doesn't really matter. It's just the clock starts when you turn it on. But anyway, so there's clocks running because you've already got a clock signal, a pulse signal, that drives the digital logic, the processor and the memory and so forth. So you may as well count those clock pulses to determine how much time has elapsed. So you can use this then for timers and counters and so forth. And it's not something you have to worry about as the programmer. It's just a function essentially that's included with the PLC. We'll start off talking about counters, but there's a lot of similarities between the two, and there's a few differences. In particular, timers and counters are the first instructions you typically deal with where you're finally doing something besides on and off. So instead of having, as Click calls it, normally open, normally closed contexts, which are either on or off, or even outputs that are on or off, set and reset, where set turns something off, reset turns something off. Instead of all of that, what you have is an instruction that has to deal with numbers, amounts of things, not just on-off things, but counting how many items has gone by. Well, you run out pretty quickly if you just use a 0, 1. Now, technically, all of the items in the PLC are zeros and ones, but the thing about a timer and a counter is it deals with more than 1, 0, and 1 that really represents a number. So we don't think about it as bits so much anymore, although that's what it really is in memory. We think of it, this collection of bits, as a number that represents in the timer how much time has elapsed, or in the counter how many items have gone by. Now, the interesting thing about timers and counters is they're typically used as outputs, but they also have inputs. So in a timer and a counter, you often have what's called a preset value. And sometimes you care about that value, sometimes you don't. But the idea is that this value is the amount that the timer or counter will go up to before it is done. Now, sometimes a timer will shut off or a counter will count no more. Most PLCs, that's not the case. In most PLCs, after the timer accumulated value has reached the preset value, in other words, after enough time has gone by so that the preset values, like let's say you set, it's kind of like setting an alarm. If you set the timer for, let's say, 60 seconds, and it comes on and it's timing 60 seconds, and after the 60 seconds has gone by, it turns a bit on to indicate that the timer's done, to indicate the 60 seconds have gone by. It's like an alarm going off. Same thing with a counter. Counters have what typically is referred to as done bits. In Click Conveyor programming, these bits are obscured a little bit, and it can be a little confusing at first. But basically, the timer and counter is something that can run. It's something that can count. It's an output thing that gets driven by logic, but then it has a bit that it sets that you can use to drive other logic. There's other differences where counters, for example, are edge triggered, whereas timers are level triggered, but we'll talk about all that as we go along. Let's investigate the system that I want to use to illustrate counters to begin with. I will make it full screen so we can see it. Here's the system. It's probably best if I give you an overhead view. I'll do that in a moment. My right clicking and center clicking doesn't work because I'm operating the computer remotely. That's a problem I'm trying to figure out and make it work. So I can't zoom and spin nicely as if I was in the lab. We've got a typical control panel here with a start button that can be eliminated, a reset button, and a stop. I'm not going to use any of those these times. There's something labeled a counter here. The counter, I would say, is more of a display, and what you could do in your PLC program is count how many boxes have gone by and display that count in this counter. I'll try to do that. I think I can make that happen. Then there's another item here. Let me zoom in on this just a little bit. It's called the buffer velocity. I've zoomed in a little too much. There you go. Here it is. It's a little knob that you can turn, and it's the buffer velocity. Now, There's a buffer conveyor and essentially an exit conveyor. I'll show you those in a minute, and that's what this is really for. Then there's a manual auto switch and an emergency stop. If we zoom out just a little bit and pivot to the top of this system, then we can get a look at it and see sort of what all is going on from a bird's eye view. So looking at it from the top, let's zoom in just a bit. And then let's move over a bit so we can see it. Again, sorry I have to use this clunky interface. If you need to use it, by the way, it's under View and then Camera Navigation. I've got it on so I can navigate. Otherwise, I would not be able to, since my right click is not working through Software Remote. So anyway, if I go back a little bit, we can kind of see the sections. The section on the left, that conveyor on the left, is the what they call the buffer conveyor, and there's what they call an emitter here that basically just drops boxes onto the conveyor at regular intervals. And then on the right hand side there's an exit conveyor. I think they called it an exit conveyor. But one other item you'll notice, if I go on over, there is a remover. I can't remember exactly what they call that. If we view the tags, you can see it. So view dock all tags. You can see what all this has. So the emitter and the remover are forced, which means they're operating automatically. The emitter will drop boxes on the conveyor, and if a box comes into the remover area, it will be removed automatically. So we don't have to worry about that. There's some other items here as well, and what's kind of interesting about this simulator is you can actually play with it. I've got it in simulation mode right now, you can see, because it's not stopped. So I can actually make some things happen. For example, I can turn on conveyors like the buffer conveyor. The buffer conveyor is not an on-off thing. It actually is a continuous variable. You can control it with speed anywhere from 0 to 10. So if I turn it on, maybe you can hear it come on. I don't know if the sound's coming through. But as I zoom in, hopefully you can see the animated conveyor belt running. Okay, so I can slow it down. Looks like we can actually make it go in reverse also if we wish. Okay. The exit conveyor is also a numerical thing. It's on. It's not just on or off. Okay. It can also be made to go in reverse, apparently. But for now, I'm just going to turn it to the center at 0.0 and get it to not move. It looks like my buffer conveyor is moving just a tad, so I'll pull it back also. So one interesting thing you can do with these simulators is control them by basically forcing things and just see how it works and what all it does. For example, if we go down a little bit, you'll notice that there's a stop in between the two conveyors, and I can force that stop on. Now that's actually the stop button. Where did they put? Stop blade is what they call it. It's an output. So I can force it on, and what you might notice, and let me zoom in just a bit, is that stop is now up. You can see it up now. When I release it, you can see the stop go back down. So I could turn it on, force it on, make it go up. I can force it go off. I'm still forcing it down, and I can also release those forces so that the PLC could control it. But this is a good way to kind of see what everything does. We could force the lights on the controls and other things. But there are some sensors as well. There's an at buffer entry sensor, at buffer exit, and at exit. And all of those, you can tell what they are fairly easily. All you have to do is just turn on the buffer conveyor. And if we can get an emitter to drop a box, say, well, why don't we turn on the exit conveyor as well. In fact, we'll make it go faster. You'll see why in a moment. Not too much faster. So now if I can get it to drop a box for me, let's see, the emitter is forced. I don't know why it's not. There we go. Okay, so the emitter is dropping boxes, and if you zoom out a bit, you can tell where those boxes are going. The exit conveyor I've actually set up to run faster, so you notice that the boxes approach the exit conveyor from the buffer conveyor fairly slowly, and then the exit conveyor really accelerates them and takes them off, and then the remover just pulls them out of the simulation. So by playing with each of the systems that Factory I/O has, we can certainly tell how they work and what they do and so forth. But you'll notice that as boxes come by this first sensor, this at buffer entry, the signal goes on and off. So the signal goes on when there's a box present. There's even a little light on the sensor so you can tell what's happening. And then as the boxes break this at buffer exit conveyor, then that triggers that particular sensor. And then at the exit, which is all the way at the end of the exit conveyor, you'll notice that there's yet another sensor to sense boxes leaving the system. Okay, so that is turning on and off as well. All of these sensors are on-off. They're Boolean type things. They're binary, whereas the conveyor speeds, for example, are outputs that are continuous outputs instead of on-off type outputs. So I'm going to shut off the conveyors and reset the simulation. Let's see, let's pull them back to nothing. Let's see, it's almost nothing. Looks like my boxes are going backwards on the... See, if I double click, no, it doesn't reset. Wonder if I can type in a number. Nope, can't type in a number. But I can double click on the item and it shows me where it's at. That's nice. Can't seem to get it. It doesn't matter, I'll just reset it. That should... Well, no, that didn't set the conveyors to 0. But for my purposes, it doesn't really matter too much. So what I'd really like to do here is, first of all, I'd like to get it set up so that I can access all this input and output with my PLC. Now, so far we've seen how to access Boolean items, things that are on or off. We haven't played around with continuous items or these numbers yet. So let's go into drivers. And you'll see I've already got it set up. If I go into the configuration, I've set up several different addresses already, so I'll show you those. Obviously the IP address of the actual PLC is required. Digital inputs at 16384 is not really a surprise. We've done that so far a bit. Those will be simulated by coil memory. So our coil memories are what we will reference in order to simulate inputs from sensors and things that are going to the PLC. And then digital outputs from the PLC are coming out of the PLC at Modbus address 8192, which is the beginning of the Y, the actual outputs on our Click Koyo PLC. Then register inputs and register outputs, you might think I haven't set them yet. I actually have. Let me demonstrate what I've done with them so you can understand. First of all, let me switch over to the PLC and open up the address picker. So just like usual, I've had to set up the inputs beginning at a coil address. So we've got the, if I go back, we can contrast the different various docked items that we've got. So we've got the at buffer entry, that's this sensor here, at buffer exit, at the exit. We've got the start button, which is down here, the stop button as well, and then the reset button. And it's actually nice to look at this in the driver's setup because they're actually labeled in order here. So now if we contrast the two, you'll see that they're in order. So we've got at buffer exit, or at buffer entry, excuse me, at buffer exit, at exit, start, reset, stop, auto switch, and then emergency stop in order. I didn't connect the factory I/O running. You'll notice there's another item here. There's this buffer velocity, and it's in blue instead of green. The green items are inputs that are on or off, or outputs that are on or off. However, the blue items and brown items are different. Those are continuous variables, numbers in other words. And you have to use a different type of memory for those because the C addresses are bits, and you can't really put them together as a collection of bits to represent a number. And the Y addresses are outputs, which are also bits, and it wouldn't make sense to put any of those together to represent a number. And so we have to use some other memory, and the Click Koyo PLC provides several different number type memories. If we begin at the DS addresses, for example, you'll notice that the data type of all these DS addresses are INT, which stands for integer. And it's common terminology to call a 16-bit number an integer. Now, technically, that's not always the case, but it's pretty common. And then for a DD type address, that's an I2, an integer 2. And what Click means by this is a long word. This is a 32-bit number instead of just a 16-bit as the DS are. And then the DH are referred to as hexadecimal addresses, and then the DF addresses are considered floating point addresses. So what I started off trying to do is I started off trying to use the buffer in a DF9 address. The reason I chose DF9 is because there were several floating point numbers already used, because this PLC has some analog I/O that's consuming some of the DF addresses, the floating point addresses. So you'll notice that DF1 through DF6 are already used, and if I remember right, it's by the modules or the analog I/O that are that's on the PLC. So I just jumped down to DF9. I gave myself a little bit of space, and I thought, okay, I'm going to try using DF9. Now, if we look at the Modbus address of DF9, it's 428689. Now, one thing I've learned is you can basically just drop this first number. So really the address I'm interested in is 28689, but remember this is the click addressing, so we need to subtract 1 from it. And if I understand correctly, it actually is less of a click thing and more of a Modbus thing. There's Modbus 0 based and Modbus that's basically 1 based. And so this is Modbus that is 1 based, which is actually preferred according to the things I've found. So anyway, 28689 would be 28688. So what I'm going to do is I'm going to try to connect this buffer velocity to that address. So if I go to configuration, the register inputs, now that's another thing to talk about. Let me go back. This number here, this buffer velocity, this is purely an input to the PLC. It's not something that can be written to, because remember that knob on the control panel? That's what this thing is. As you turn up that knob, you're sending a number to the PLC that is a higher number. How could the PLC write something to that knob and make the knob move? That would not happen, right? This is just a dumb knob. There's no motor on it. So it's a pure input to the PLC, and that's why it has the color of blue. Now all these other items over here, these other 3 items, the buffer, conveyor, exit conveyor, and counter, they all have blue and brown. And what that indicates is that these are areas that the PLC can, that can be written to or read from in the PLC. Anyway, so this particular item here, this buffer velocity, is the knob, and I'd like to put the knob in on address DF, I think it was 9, which I don't remember the number now. Let's see. The Modbus address 28688. So let's try putting that in and see what happens. So configuration, that's an input to the PLC, so 28688 is the number. There's only one of them. And so let's go back and see if that works. Now how can we tell if it works? Well, what we've got to be able to do is have the simulation running and twist the knob, and then see if the PLC can sense that twisting knob. So I've got the address set up. I'm going to dock all these tags, or undock them really, clear them so that I don't have to see them right now, and then rotate down where we can see the control panel, and I guess move over there a little bit, and maybe zoom in just a bit so we can see it. Let's see, I think I need to rotate around maybe this way. That's good enough. We can see it now. Okay, so there's my little knob that I can twist, but the question is, does the PLC see this? I mean, right now we're in simulation mode. This information should be sent to the PLC. So DF9 is the address that it should be coming in on. I'm just going to cancel this because I was looking at just addresses. Now notice that the PLC is in run mode with a blank program. If I scroll up, you'll notice that this is rung 1 and it just says end. So what I'm going to do is hit monitor and data view. I've already set up a data view to view some interesting addresses, and one of the addresses I'm viewing, or one of the addresses I want to view, is the DF address. I took it out a moment ago while I was practicing this or planning it. So now I'm going to put it back in. DF9, remember that's the Modbus address that I chose. Let's double check it, make sure it makes sense. What was it? 28688. So that's what I typed in, and that's what I want to use. And what we're going to do is monitor it, right? So it's a real number. It's not an integer, a real. In other words, it's a floating point number. The PLC is in run mode, so we've got Modbus communication going on. And if I turn this knob, so I've turned it up, let's look and see if that changed anything in my data view. It looks like it did. Now, I don't know exactly what that number means. Let me move this off to the other side so I can actually see what's going on here. So now I should be able to go over and move this knob, and let's see what happens. So the number is changing, but it doesn't make any sense, right? It's changing 1.4, 2.8, 4.2, 5.6, E negative 45. I suppose I could use that, but it's inconvenient. I mean, certainly this is a bigger number, 1.4 E to the negative 44th, than this number, which is, well, no, that's 0. Let's see. So somewhere low, like 5.6 E to the negative 54th. But it's really just not operating the way I would like. So what I'm going to do instead is try connecting this to a different type of address, maybe an integer address, and see what happens. Okay, so DS4, for example, might be a good address. So let's see. I'm going to close this temporarily, go to the address picker, and, oh, that's the wrong comment. Go to the address picker and look at DS one section, show me Modbus addresses, and it looks like that DS4 is on address 4, which we can ignore, and then 4 zeros 4. Okay, so that would be address 00003 because we've got to subtract 1. So this is where I'm going to try putting the let's call it the buffer knob, okay, because that's what it really is. It's the buffer knob. And we'll say, okay, we've named it. Now let's go over here to Factory I/O and put that address into our drivers and see if the number we get from it makes any more sense. So we'll put this back to, let's see, 1, 2, 3, 4, 3. Remember, I could neglect the 4 at the beginning. When I click off, it just gets rid of the leading zeros, and it's just address 3. So now let's go back. And the knob is actually up above 0, so if we go to monitor now and data view, looking at the DFs and the DSs, it's a custom view that I made. Let's see. Now we've got a 3 here on the buffer knob. Let's try changing it and see what we get. So you see that it goes up nicely. It goes up to 10, and now it comes down nicely to, well, that's the other side. It comes to 0. So I much prefer using the DS address because it's easier to interpret and use. So I'm just going to stop monitoring this one. Let's see. I think you have to right click and delete the row. There we are. So I can get continuous data into the PLC. As a matter of fact, I can write out a count to the counter. You notice that this address in DS3 contains the number 9. And guess what number is shown here? Now, I don't know if I can change the value. Let's see. No, there's no override. If I edit, does that allow me to? Let's find out. Won't let me type. Let's see. View override. Still can't type it, so let's override on. There may be a way to do it, and I just don't know what it is. But I can show you how to put a number into memory if necessary. So let's start there. Let's change the display on the counter. Let's change our program. And what I'm going to do is use a copy command. I'll get to the counters here in just a minute, but let's just take a constant number, like let's take 12. And let's put it into that counter address. And it's not really a counter, it's more of a display, like I said. So I'm not really playing with counters yet. I'm playing with displays that are called a counter in the simulation. So I'll say OK. And all this copy command does is take a number or a memory address and copy it into another memory address. That's all it really does. And then I'll need an end instruction at the end of my program. There we are. And now I'll download it to the PLC. It will say you want to put it into stop mode. I'll say yes. It downloads. It's not a long program at all. Shouldn't take a second. Transfer is complete. And now we'll run again. So now you notice that the counter in Factory I/O has changed to 12 because I'm just writing that number into DS3, which is a particular Modbus address that Factory I/O is monitoring and responding to. Okay, so I can write out information in a continuous fashion, and if I really wanted to, I could turn on the conveyors with this. For example, I may as well, after all. Let's see. Instead of DS3, let's write out, the conveyors only go from, well, -10 to +10, and honestly I haven't figured out a way to give it a 10 number via the Modbus address yet, but that doesn't matter. I'm just going to put it at a speed of 5. I don't really want to control these conveyors in the backward direction anyway. And I'll just turn on the exit conveyor, for example. There we go. Alright, so now what I'm going to do is write the number 5 into address DS2, and let's download that to the PLC. Factory I/O is running, and what we should see is the exit conveyor come on. So we'll go over and look at it run. Transfer is complete, put it in run mode. Okay, there we are. So now if we go over to the conveyor, it looks like it might make a liar out of me. I don't see motion yet. I see some reverse motion. So that indicates to me that I forgot to unforce it. So if I dock all tags, yeah, right now the exit conveyor and the buffer conveyor are both forced because I was messing with the knobs here to change the speed. So if I release both of them, I don't have to release the buffer, but the exit conveyor, if I release it, now it's going forward at that rate of 5, which I could change all the way up to 10 and it would actually respond. I've tried putting numbers larger than 10 in there, and it just runs at maximum speed of 10. So this does work. I can copy, numbers into the correct address and get things to happen in the simulator. Now, all of that being said, all I've done so far is work with numbers rather than just on-off things. So why don't we do this? Why don't we set it up so that, let's set it up so that we are putting boxes out on the buffer conveyor and then sending those boxes on. But let's set it up, and I'll just control the conveyors manually with forces. I don't want to bother with programming it too much. And let's add a counter to count the number of boxes that go by. For example, let me count the number of boxes that come onto the buffer conveyor from the emitter, and then have a secondary counter that counts the number of boxes on both the buffer and the exit conveyor. So I'm not going to use the intermediate sensor that senses boxes going from the buffer to the exit conveyor. I just want to demonstrate how you use counters. So what I'm going to do is actually force both of these. I'll turn the entry conveyor on fairly slowly. The exit conveyor, I'll go ahead and force it as well. Let's see, and make it go to a little higher speed like I had before. So now I really don't care about seeing the tags anymore. I've already copied the correct Modbus addresses for all the sensors, so they're already named in my software. I already showed you that, but I'll show it to you again. So over here in the Click Programming software, the inputs of interest I've already named. So I've got the sensors at buffer entry, at buffer exit, and at exit. The two I'm going to be concerned with are at buffer entry and at exit, because that spans both conveyors. That's from the beginning of the first conveyor to the exit of the second conveyor. So I'm going to shut down the tags so I don't have to look at them, and then I'm going to go to an overhead view because I think that's probably the easiest way to understand what all is going on here. Now let's see, how can I turn this? Let's see. There we are. And if I zoom out just a bit, hopefully we can get a view of the whole thing. That overhead light's in the way, but it looks like we're avoiding it well enough. Okay, so we can see on the left, it looks like I got some boxes that are just hanging out here that fell off somehow as I was playing with it. So we can see the emitter is putting boxes on the buffer conveyor. The sensor senses those boxes as they go past, and then the exit conveyor, its sensor also senses boxes as they leave. So what I'm going to do is add some counters into my program. I'm going to get rid of the copy because I'm not trying to control the conveyors. And we have to select a counter number. So if I click on the addresses, what you'll notice is that you have a lot of counters to choose from. They're numbered CT1, CT2, CT3, so on and so forth. So this will just be counter 1. I'll just pick it, and I could name it if I wanted to, and I can give it a set point. Now the set point is just basically how many things do you want me to count before I tell you that, hey, I'm done counting, or the count has reached your preset value. The counter will set a bit for me, and I'll show you where those bits are here in a second. But well, in fact, you can see it here. CTD1 is actually the current count. It's where in memory the count is actually stored. And then CT1 is the bit itself that indicates the counter is done. Now, unfortunately, the counter number is also CT1. So there's a bit of confusion between the name of the counter, which is CT1, and the done bit, which is CT1. But it doesn't matter. As long as you understand that, it's fine. So I'm using CT1, which will be a done bit called CT1. And I'll set a set point. Now, you can set all kinds of set points. Let's try, if I start typing numbers, you see what type of value it assigns. It assigns an integer. If I get too large, an integer is a 16-bit number, and it can hold up to a maximum value of 65535. If I go above that, like right now I'm at 10,000, if I go to 100,000, 100,000 is above 65535, and what the software does is it says, okay, I've got to set aside a value for you that is an I2, a 32-bit number, and if I just keep adding zeros, finally it says, okay, I just don't have enough memory to store that. You can't put that, so there's an upper limit to how many items it will track, and then set the done bit, you know, how many counts it's willing to count for me. So an I2 being a 32-bit number, I don't remember the maximum it can go up to. I think it's about 4 million or so, something like that. Maybe it's 4 billion. I don't remember. You could calculate it. But anyway, I'm just going to make it go up to, I don't know, maybe 100 boxes, because that'll go by fairly, let's see, maybe 50 or so. Let's do that. Now, this is a count up type counter. They've got count down counters, and they've got counters that will count up and down. I'm going to start by just using a count up counter. Now, like I said before, these counters are edge triggered. What that means is that the rung preceding the up input has to transition from low to high, and when that happens, the counter will increment the count in CTD1. When that input rung goes from true to false, the counter doesn't do anything. Now, you might look at this and say, well, I guess I need an edge contact to sense that transition from low to high or high to low. That's not the case. You actually only have to put on just an instruction to look at memory and decide whether or not it's on or off, and the counter will automatically detect when that rung goes from false to true. And so what I'm going to do is I'm simply going to reference that sensor at the entry to the conveyor. So I'm going to reference the at buffer entry sensor, and now whenever the sensor over here at the buffer entry senses a box going by that's just been emitted, what it'll do is it'll transition from low to high. It goes from low, I don't see a box, to high, I do see a box. And as soon as that happens, which will happen on the leading edge of the box, the counter will count up. Now, I'm purposely going to leave this reset off because a lot of times students forget to connect it, and for whatever reason, in Click Koyo programming language, you have to connect it up. But I want you to see the error that the software gives you when you don't connect it. So what I want this counter to do is just count the number of boxes that go by. It's that simple. So let's try that. I think I've got everything set up except for that reset. I'll tell it to download, and it says, oh, there's a problem. There's a syntax error. What you have to do is, let's see, well, the operation has to be canceled. It doesn't give you very much information. But down here in the compiler window, if you can read this, it says main program rung 1 error C0202 row 3 column AF missing line connection. So I can tell it's definitely on rung 1 because this tells me that. Beyond that, it says missing line connection, which suggests I have to have something connected to this reset. What the reset does is it resets the value in CTD1. If you've been counting items and for whatever reason you need to reset the count, this is the line that you have to make go from low to high to do it. So if it is edge triggered, I can simply connect this back. So let me just connect this wire back, and it looks like there will be a constant reset because we've got a constant true signal on this line. But if it's working the way I think it should work, then, you know, if reset is also edge triggered, then what should happen is this counter should simply work now. So let's find out if that's the case. So I will download this to the PLC. It says there's an error. There's no contact in the reset input. So what it's saying is I guess it's saying that this is not edge triggered, it's level triggered. So I'm going to throw in just a junk contact. Now maybe I'm doing this wrong, maybe there's a better way to do this. I don't know. This is what I've just always done. And so I'm going to just choose an address, like for example one all the way at the end of all the bits, so I know I'm not using it. And the coil memory goes all the way up to C2000, so I'll just grab the last one. It's not something I'm using, so it'll never go true, and we'll see if it likes that well enough. Yeah, no more errors and warnings. So now it will actually download. And what should happen as the boxes go by is we should simply see the count increase. So we'll turn into run mode, and you see the current value of CTD1. I was using this before, so it already had some value. I suppose if I forced C2000 to go high, I could reset that count. Why don't we do that? We've got forces. So let's monitor override view, and what I will do is just grab address C2000. So C, highest number I can get so I don't have to scroll forever. Pull it down, C2000, OK. And current value is off, so what I'm going to do is turn it on, override, and that worked. Now you notice as long as I've got it on, it's held on and it's resetting the count continuously. So this is level triggered instead of edge triggered. But you'll notice that once I unforce this, once I turn the override off, and I should be able to just, let's see, current value is on. Let's see, if I delete this, will that get rid of the force? No, I've still got some, it's still forcing that. So this is true. Oh, I've turned it on, I haven't turned it off. Okay, no big deal. So what I'll do is go in and force it. There's nothing to change its status. So monitor, override view, and then let me grab that address again. It's just a simple memory address, so that's why I'm used to inputs which will change automatically because they're referencing the actual input card. But this is just a memory address. So let me get back to that address. Suppose I could type it in, it might be faster. There we go, open it up, and we will make it turn off. We'll override that. Let's see, write all new values. Yeah, do it. And so now it's off, and now I can remove that force. And you see that the counter is now counting up. So it's just counting how many boxes go by. And while I've been talking, 10 boxes have gone by. Now one interesting thing is that you could make this counter self-reset. Because remember, there's a bit that comes on once the count has been, or once the preset has been achieved. So right now we're at 22, that's less than 50. So the bit is not on, indicating that we're done. So let me change this. I'm going to change it to CT1, which is the, well, let's try CT1. Wrong keyboard layout, there we go. So I'm going to change it to CT1, and I'm going to download it to the PLC. Now what will happen when I do this is that the PLC will use the reset bit from the counter itself to reset the counter. So you see we're at 45 boxes, 46, 47. You'll see this done bit grow true. We're at 50, and boom, it happens in one scan. It resets it back to 0, see? So this is a self-resetting counter. So we'll just leave it that way. The other thing I wanted to do was have a counter that counts how many items are on the conveyor. So what I'm going to do is reset the simulation, and I'll reset it again here in a minute because I don't want anything on the conveyor. I'm going to use a count up and count down counter. So if I grab a counter, put it here, I can't use CT1, it's already used, so I'll use the next one in line, which is CT2. And then my set point, I really don't care. I'll use 1,000 or 10,000. It doesn't really matter. But I'm going to make it a count up and down counter. So say OK. Now I have to actually connect wires to all of these as well. So let me go ahead and draw them. And let's see. You have to be careful. Don't click this one because it'll make a connection down. That'll give you a weird kind of error. But if you click off to the left, you can connect the wires all the way back, and then we can put instructions on them, because again, it will not accept me just connecting wires, having an unconditional reset. Alright, so still the up and the down are edge triggered, but the reset will be level triggered. So I'm not going to put anything particularly interesting in for the reset. I'm just going to go back to C2000 and use it. I'm not going to make this a self-resetting counter, because what I'm going to do is just make it count how many boxes are on the conveyor belt. Now, if I use the at buffer entry set of contacts, or the sensor that's sensing boxes come onto the buffer conveyor, then that will make this count go up. But there's another sensor at the end, and if I look at the address for it, let me grab the type of instruction I want. If I look at the address for it, fortunately I've named these so I can tell which one is at the exit. You see, this C3 is at the exit of the exit conveyor. So say OK, hit OK. So there we are, and that should make it go down. Every time that exit sensor is triggered with an edge trigger that goes from low to high, that should decrement the count. Okay, so I am going to download that to the PLC, and oh, there's a syntax error. What did I do? Oh, no unconditional end. I overwrote it and forgot to add it back in. So there we go. So now I've got the unconditional end, and now we can download the program. I got to go to stop mode again. There we go. And transfer is complete. And go to run mode. Now, as we go to run mode, I'm going to reset this thing. And I don't like this because the counter does not represent the actual count. So I'm going to stop this. That'll reset it. And then over here, what I'm going to do is see if I can just manually change the number in memory. Let's just see if it will let me. I'm not sure if it will let me. I'm going to go to the CTD addresses, which is where all the counters store the number that they have. And it looks like the number in CTD2 is not showing up. There's a nickname here. I can show the Modbus address for it, but that's not really useful because I don't care about making factory I/O know what the count is. I guess I might actually. That might be interesting. We'll do that in a second, because I was going to try and display the counter on the display, the control display. In any case, let's see. Let me just go ahead and use this C2000 to force a reset, and that'll be the quickest way to demonstrate this counter and what it's doing. So we'll go to override view, we'll grab C2000 again, and maybe I could just wire this up. You know what, let's just do that. Rather than going through all these forces, why don't I just wire this to the reset button? I've got it referenced. So I'll just grab this, go to memory addresses, look at the C addresses, and the reset button is right there on C5. That way I can just push a button in the simulator and reset the counter. So now if I hit run, alright, let's see, this is going to be a little bit of a trick because I'll have to reset both pretty rapidly. So let me rotate down. I'm not quite that far down, I'm below the floor now. There we are. Go over to the control panel. Things get a little louder as we get closer to the machine. Let's see if we can pivot down a bit, zoom in a little bit, and go over just a touch. There we go. So if I hit reset, I've got to download and monitor my program. Hang on. So let's download this new program. I forgot to do that to the PLC. We'll put it in run mode, see where our count's at, and see if reset actually causes the count to reset. There we are. So we got 17 on the conveyor in theory. So if I hit reset, sure enough, that does reset it. So I'm going to reset the simulation. And now, unfortunately, what you could not see was that when I reset the simulation, that took all of the boxes off of the conveyor, and so you'll notice that if all the boxes were off and I reset the count, then this counter would start counting up when a new box comes on and count down when an old box goes off. If you watch this, sometimes you'll see the count change a little bit, where there's actually just 4 on the conveyor at once. Let me go to the overhead view again so you can see this. Scroll back just a tad, get it oriented properly. And so now you can see that there are in fact 4 or 5 boxes on the conveyor at a time, and you see these lights flashing indicating that boxes are coming on or boxes are leaving. And of course I've set it up so I can reset it with the reset button, which is a little more convenient. The preset value is 1,000. Notice the preset value doesn't really matter here, right? Because all I'm doing is counting how many boxes are on the conveyor. Now let's see if this works. Let's go and view the tags. So we'll dock all tags. And let's slow down the conveyors. If I slow down the conveyors, especially the exiting conveyor, then there will be more boxes on the conveyors eventually. The density will increase. As a matter of fact, the exiting conveyor is going slower than the entering conveyor. So let me slow them down, hopefully where they're closer and maybe even match. Let's see, I'm going to try to get 1.6 down here. There we go. So now they match, and I count, let's see, 1, 2, 3, 4, 5, 6, 7 or 8, and sure enough the count is accurate. Okay, and maybe it's actually 9 and I miscounted a bit, or maybe they're a little more dense now, both have slowed down. So it looks like this counter is doing what I want it to do. It's telling me how many boxes there are on the conveyor. So to recap, what we've learned is that the up and down inputs to counters are edge triggered. In other words, when the logic, and it can be a lot more complicated than what I've got here. It doesn't have to be a single instruction. It can be an and, an or whatever you want it to be of multiple different conditions. But when the rung goes true, goes from false to true in fact, the up will be triggered or down will be triggered or whatever it's connected to in the counter will be triggered to either increment or decrement the count that is held in a CTD type of address that's associated with a bit in CT1 and also the name of the counter CT1. And so then reset always has to be connected. Why? I don't know. That's just what they do. That's what Automation Direct does. And you can make a counter self-reset as I've done here. So I've used the bit from the very own counter. You could make this counter reset when the other counter is done, for example. You can reference whatever logic you want here that indicates that it's time to reset the counter. Of course here I connected a reset button because I just needed to manually reset it. So that's how counters work. They're fairly straightforward. They're easy to use. The key is understanding that they are edge triggered and not level triggered. And then beyond that, that you can use the information, the bits from a counter, in order to know when a certain number of events have occurred, like a certain number of boxes have gone by. And so it looks like we just rolled over the 50 while I was talking there, and 50 went by. That was the event that triggered the reset. And of course that bit can trigger other things to happen. Maybe you're palletizing something. You've got a pallet and you're putting boxes on it. You need to count how many boxes are going onto that pallet. I believe there's even a simulator like that in this program of Factory I/O. And so you need to count how many boxes you're putting on a pallet. Well, a counter is perfect for that because your PLC program is in control of the system, and it knows, if you will, when it has put a box onto the pallet, and so it can simply increment the count when that happens. Of course, you have to figure out the logic. Well, how do you know that a box has been placed? Maybe it's that the robot that's doing the placing is complete with that stroke or something and has its own type of what I would call a done bit to indicate that its movements have been completed. But you have to work out the logic yourself, which is the essence of PLC programming. So here's another little piece that you can use, a little piece of the puzzle. It's a counter, counts up events, whereas timers count up time. So I'll demonstrate timers as well for you later.